Welcome to a very practical episode of Intelligent Machine Monitoring. Today we have Wolfgang back here in the studio. You know Wolfgang from a previous session he gave on the sensor positioning, the best practices for sensor positioning on reciprocating compressors. Today is sort of a follow-up session where we talk about the cable length between the sensor and the data acquisition unit. Right?
That's correct, Jost.
Okay,
yeah.
Enjoy your show.
Thank you, Jost. So, which aspects do we have to consider when it comes to the maximum cable length of the signal cable between the sensor and the data acquisition card? First, regarding the signal quality and also regarding the intrinsically safety. In this video, we are going to have a look at ICP acceleration signals, ICP for integrated circuit piezoelectric, which is the most commonly used technology in the industry. The standard recommendation for maximum cable length is 300 meters for two reasons. Number one, 300 meters or 1,000 feet is easy to remember. Number two, with 300 meters you are on the safe side. There's not yet an impact on the signal quality and you have the full frequency response. So this standard recommendation for the maximum cable length applies for cable in the non-hazardous area. So why do we talk about the maximum cable length at all? For this, we have to look a little bit into the physics of a cable. So if we take a signal or a cable pair, for example, in a multi-core cable, where we have here the cores and here we have got the shield, each cable has a capacitance between the cores and between the individual cores and the screen. So the total capacity of a cable is the sum between the capacity between the cores and the capacities between the screen. This capacitance, of course, is larger the longer the cable is, and this capacitance, together with the impedance or resistance of the input card of the sensor, builds a low-pass filter. A low-pass filter, which, here I draw a diagram where we have got the frequency here and the amplitude here, which cuts off higher frequencies, and we are interested in this point, 3 dB, which is the cutoff frequency of a low-pass filter. Now, what is a cutoff frequency? Which frequency do we need? From our practical experience on reciprocating compressors, we say that we need 10 kilohertz. So if we look at the valve activities at a reciprocating compressor, suction valves, discharge valves, the opening and closing, if we have, for example, a broken valve plate, you want to measure frequencies up to 10 kilohertz. The same applies for the acceleration sensors that we mount on the crosshead guide. So when you have, let's say, a loose connection at the crosshead, between the crosshead and the piston rod, whether there is a crack or anything else, the frequencies might reach up to 10 kilohertz. If we look at centrifugal machines, for example, at gearboxes, we can make a simple calculation. If we assume, for example, we have a gear with 60 teeth, and this gear has an RPM of 6,200. If we do RPM, so if we make a calculation, we get to 6.2 kilohertz of the gear mesh frequency, and we are well, let's say, advised if we then have a frequency range of maximum 10 kilohertz. Now, how do we then calculate the maximum frequency of a given signal length, cable length? There are two ways. One is the calculation of a low-pass filter, and the next one is using a nomogram. I prepared here such a nomogram. A nomogram has been developed in the old days when the engineers didn't have yet a pocket calculator, when the engineers didn't have yet a computer, or when the bricklayers built such a nice factory like we have here. So what they did is they, for a complicated mathematical formula, they make alignment, let's say a graphical alignment chart. And we see an example here. So on the x-axis, we have the frequency here in hertz. And on the y-axis, we have the relation between the maximum output of an acceleration sensor, volt, and the constant current of the input card, IC, which is 10 milliampere, and we deduct 1 milliampere. So if we have here 5 volt divided by maximum current of 10 milliampere minus 1 milliampere, we get to a value of 0.55. In this nomogram, then we have different graphs that were previously calculated for different capacities of the cable. We see it here in picofarad, 6,000, 10,000, 30,000, 100,000 picofarad. A standard signal cable has a value of around 120 nanofarad per kilometer, yeah, which is 120,000 picofarad per kilometer. So with a maximum or with a cable length of 300 meter, we get a value to 36,000 picofarad. Now we already know two variables. We know the relation here between the output voltage of the sensor and the ampere, the current of the input card, 0.55, and we know the capacitance of the cable. So if we now draw a line of this value up to the graph of this cable, this around 30,000 picofarad, and we go down, we see here we land at the value of 10 kilohertz. So we know for this given cable with this given capacitance, we are fine having a length of 300 meter. And we do not have the cutoff frequency lower than 10 kilohertz, the 10 kilohertz that we want to measure. So this is regarding the signal quality. If I resume, we need, from our experience, 10 kilohertz to do a decent monitoring. Each cable, by the physics, has a capacity, and with the impedance or resistance of the input card builds a low-pass filter. And we have to limit the cable length in order to have a decent monitoring for all the signal analysis. The next point I want to mention is regarding the intrinsically safety. The machines that we monitor are frequently operated in hazardous areas. That means they might be surrounded by an explosive atmosphere. And in order to avoid explosions, there is a way to limit the energy that the input card drives to the sensor or gives to the sensor. And this is done by, for example, by barriers or galvanic separation units that limit the power going to the field, intrinsically safety. And the concept is that the inductivity of such an input card is greater than the sum of the inductivity of the sensor plus the inductivity of the cable. In this case, it's quite simple. We have an inductivity of the input card 4 millihenry. We have an inductivity of this given cable 1 millihenry per kilometer. This one, the 66 microhenry, we can neglect, so it is like 4 kilometer that are allowed regarding the intrinsically safety. If we look at the capacitance of the cable, the input card, which is then the associated device, having the barrier, has a capacitance of 85 nanofarad. The input or the capacity of the sensor is 1.2 nanofarad, and the capacitance of the cable is 120 nanofarad per meter. If we now make the calculation, we subtract 1.2 from the 85, we come to 84, and then we divide it by this 120 nanofarad per kilometer, we come to a length of approximately 700 meter. That means for this given sensor, and this given input card as associated device, the maximum cable length that is allowed is 700 meter. so we are safe as well. Now,
what can I do when I need to achieve a longer cable length?
Yeah, if you want to achieve a longer cable length, then you would have to look for a cable with a lower capacitance. Okay. Of course, cable with a lower capacitance are more costly, expensive, and then you have to do your calculation, your math, so which is more economic for you, going to a longer cable or maybe having this acquisition unit installed in the field.
Okay, closer to the machine.
Closer to the machine.
Do not have
That's correct.
any cable length issues.
Yeah.
Okay, great. Anything more to add?
No, I think that's all for a rough overview.
Okay, thank you for that, Wolfgang. Hope to see you here again.
Okay.
Hope you enjoyed what you have seen today and what you have learned today. So stay tuned here at Intelligent Machine Monitoring.